So before going into the MLCT and LMCT, first I want to tell a few points about charge transfer spectra and DD transitions. So DD transitions appears at less frequency region, whereas charge transfer bands appear at a more frequency region. So this is because of DD transitions are spin allowed but Laporte forbidden, whereas CT bands are allowed both, spin allowed as well as Laporte allowed. So when we have a three metals like M+7, M+6, M+5, so these are the three metals they have asked in examination point of view. So they have asked that which one will appear at a more frequency region. So that is the question. So this is very simple. So when oxidation state increases, the size of the metal will decreases, that we know that. So on this basis, this M+5 will be more in size. Okay, so now, so we have electron here and the nucleus is here, and if we see the nucleus is here, it's very close to the outer electron, so this can easily attract this electron. Okay, whereas in this case the distance is more, so because of that reason, so it cannot attract this electron. For that we need to give some energy. In this case, where size is more, there we need to give some energy. Okay, so now here we no need to give any energy, but here we need to give little energy, and here we need to give more energy. So now we will arrange in the energy order. So since here we are giving some extra energy, this M+5 will be having more energy, then M+6, then M+7, and the question is which appears at high frequency region. High frequency region, this is the question. Among these three, which appears at high frequency region. So now this is the energy order. We know that energy is directly proportional to frequency, right? So high frequency region will be M+5, low frequency region will be M+7. If they ask which one will be more which one shows more wavelength, then we can say energy is inversely proportional to wavelength. So on this basis we can easily identify the answer. They may ask this kind of question, MnO4 minus CrO4 minus 2 vanadium O4 minus 3. So for when they ask question like when they ask this kind of complexes, you just apply the same concept. So when size is more, there we need to give more energy, because of that this will be having more energy, whereas when size is less, we don't need to give energy, that will be having a less energy. And then we can also say that more oxidizing power and less oxidizing power, more oxidizing power and less oxidizing power. So among these three, M+7, M+6, M+5, so which one will be having more oxidizing power? So more oxidizing power means the metal which is a more electron deficient. So here it's a +7, so this will be having more oxidizing power compared to this. So we can also say that if ligand electrons are there, it can easily attract the electrons from the ligand. So that means metal is oxidizing the ligand. That's why M+7 is having more oxidizing power. So the metals which is having more oxidizing power, they comes at a less frequency region. Okay, and complexes which are having less oxidizing power, they comes at a more frequency region. So this I just want to highlight this point. And now we'll go for the first we'll go for LMCT charge transfer spectra. So mostly we have a sigma donors and pi donor. These two shows this kind of LMCT. So if they ask question cobalt NH3 6 3 plus, how many transitions possible in LMCT spectra, LMCT. So this is the question, so you need to answer for this. So if you want to answer this kind of question, you need to know the MOT diagram. Okay, the MOT diagram looks like this. This is the n-1 d orbital, that is T2g and Eg. This is T2g, this is Eg, and this is T2g, and T2g we will denote by pi star, Eg we will denote by sigma star, and these are the sigma ligand group orbitals. Okay, so if it is here we are talking about the sigma donor. Pi donor we will talk about about pi donor we will talk later. So these are the homo orbitals of the ligands. Okay, so cobalt NH3 6 we have, that means cobalt NH3 6 is having a D6 configuration, right? So that means we have a T2g6 Eg 0. So here all electrons are filled. Okay, and from homo orbitals to this T2g orbital, this transition is not allowed because all the electrons are filled, whereas in case of Eg is vacant is there, so this transition is allowed. Okay, so only one transition is allowed, that transition is sigma LgO2 sigma star, or we can say Eg. Okay, and sigma LgO2 pi star or T2g, this is not allowed because T2g orbital is already completely filled. Okay, so because of that reason this transition is not allowed. So here we are talking about only sigma donors. About pi donor I will talk later. And we have another example that is so we have chromium NH3 6 3 plus. So this shows D3 configuration. Okay, here also NH3 is a sigma donor. This is n-1 D. This is includes T2g and Eg. Okay, this is sigma ligand group orbitals. This is the homo. So this will be T2g, that is pi star. This is Eg, that is sigma star. Now we have D3 configuration. D3 means T2g3 Eg 0, and here we have 1 2 3. And now see, in the T2g orbital also we have a vacancy. So here one vacancy. Okay, so here one transition is possible from T2g to homo orbital to T2g. Another transition is possible from homo to Eg, and in this case we will get two transitions. So sigma LgO2 pi star, we can say T2g, and sigma LgO2 sigma star, we can say Eg also. So in this case two transitions are possible, whereas when we have a cobalt NH3 6 3 plus, in this case only one transition is possible. So this is about the sigma donors. We can say example ammonia is a sigma donor. And now we'll go for the pi donors. So pi donors also shows this ligand to metal charge transfer spectrum. About the pi donors. So now pi donors also act as a sigma donors. This we know that. Okay, so now we have a n-1 d. I forgot to tell one point here. In this case I forget to tell one point. So from d0 to d5 we'll get two transitions, because d0 includes this kind of configuration. So these are the homo orbitals of the ligands. So one transition is possible from here to here and here to here. And d5 also, when we have a d5, because charge transfer is only for the strong field low spin complexes. Orgel diagrams are for the high spin complexes. Charge transfer is for low spin complexes. So d5 will feel like 1 2 3 4 5, and here one vacancy is there. Here one transition is possible, another transition also possible. So come for the d6. So from d6 to d9 this transition is completely ruled out, because already filled, completely T2G is completely filled here. Okay, so because of that reason this transition is not allowed. Only transition allowed is homo to EG orbitals. From d6 to d9 only one transition is allowed. From d0 to d5 two transitions are allowed. So now here we have sigma donor. We can take as a fluoride, chloride, these are chloride, bromide, iodide. So these are the examples for sigma donors. So we have n-1d. So this includes T2G as well as EG. And here we will be having a two group orbitals. So this will be a pi ligand group orbitals, and this will be sigma ligand group orbitals, because whatever ligand we are dealing now, that is acting as a pi donor as well as sigma donors. This is for pi and this is for sigma. Okay, so now imagine that I will generalize the points here also, from d1 to d5 and d6 to d9. Okay, so imagine that we have a d3 configuration, 1 2 3. So now there is a transitions from, this is a pi homo and this is sigma homo. So since both the places vacancy is there, so from here to here one transition, from here to here another transition. From sigma orbital also two transitions possible, from here to here, from here to here. So from d1 to d5 total 4 transitions are possible. From d6 to d9 only 2 transitions are possible, because from d6 to d9 T2G is completely filled, only electrons goes to the EG orbitals. Okay, so I will write all the transitions here. Sigma LG was to pi star and sigma LG to sigma star, pi LG was to pi star and pi LG was to sigma star. So these are the transitions are possible for from d1 to d5. So from d6 to d9 only these two transitions are possible, from d6 to d9. Okay, so this is about the pi donors. So when we have a pi acceptors, this pi acceptor shows MLCT, metal to charge transfer spectra. Okay, here is not matter that how many electrons are there. This is n-1 into d, this is T2G, this is EG, and this is the LUMO of ligand. Okay, so here two transitions. Okay, in pi acceptor in all the cases two transitions are possible, from T2G to EG one transition, from T2G to HOMO one transition, LUMO one transition, from Hg to LUMO, another transition is possible. So this is about the pi acceptors. Mostly pi acceptors shows MLCT only, and I will take some of the questions here. So we have oxygen, sulfur, selenium and tellurium. So among these four, which shows LMCT more? Okay, so here we just LMCT, we can say inversely proportional to electronegativity. So here oxygen is more electronegative. The more electronegative atoms will not show LMCT. This point we have to remember. So since from in the group from top to bottom, the size is increasing. That means electronegativity is decreasing. So this is the least electronegative in nature. So because of that, tellurium shows more LMCT compared to selenium, then sulfur, then oxygen. So LMCT we can say inversely proportional to the electronegativity. And we can see some questions like we have MnO4 minus CrO4 minus 2, vanadium O4 minus 3. So we need energy order, lambda max order, you can say more oxidizing power, more reducing power, so all these things we can just remember. We know that energy is directly proportional to frequency and energy is inversely proportional to lambda max. So based on this concept we can answer everything. So we know that MnO4 means manganese is present in the +7 oxidation state, Mn +7, and chromium +6 here, and vanadium +5 here. So the size, if you see the size, manganese will be small size, chromium will be more, and vanadium will be more size. So now we have a ligand electron we have here. Okay, so the nucleus is here. Nucleus is very close to the outer shell electron, so this can easily attract this electron. So for that we no need to give any energy, whereas here nucleus is somewhere here and electron is here, so is far. We need to give some energy to this vanadium +5 in order to attract this electron. So first we'll arrange them in energy order. So we need to give more energy here, less energy, and no energy. So energy wise, vanadium +5 is more, chromium +6 is more, and manganese +7 is more. Okay, so energy order we got it. Vanadium O4 -3, and chromium O4 -2, MnO4 minus, and lambda max. So by this relationship we can say that MnO4 minus, CrO4 -2, vanadium O4 -3. Okay, so now we have finalized 2, and now we'll go for the oxidizing power. So this is very important. Just remember that complexes which is having less size. Okay, I can say in another way, this is the nucleus and this is the electron. So this can easily attract this electron. That means this is having more power to attract this electron. Means after attracting this electron is coming from here to metal. So here what is doing metal? This metal is oxidizing the ligand. That means small the size, more oxidizing power. And bigger the size, more reducing power. Is very important. So according to that, more oxidizing power will be MnO4 minus, then chromium O4 minus 2, then vanadium O4 minus 3, and reducing power will be opposite, vanadium O4 minus 3, chromium O4 minus 2, MnO4 minus. So this kind of questions they frequently ask in examination point of view. And we see that manganese, MnO4 minus, manganese, technetium, I think chromium, molybdenum, tungsten. Sorry, this is vanadium, V. Made a mistake, V. Okay, so these are the I think manganese, technetium, yttrium, zirconium, niobium, molybdenum, technetium, lanthanum, hafnium, tantalum, tungsten, rhenium. Okay, Re O4 minus. Next to scandium, titanium, vanadium, chromium, manganese. And we have here vanadium O4 minus 3, niobium O4 minus 3, and tantalum O4 minus 3. So now in all these three cases, oxidation number is same. It is plus 7, it is plus 6, here it is a plus 5. Okay, so in this case, first we'll talk about this. We have a MnO4 minus, TCO4 minus, ReO4 minus. In all the cases, oxidation number is plus 7, but from top to down we know that size will increases. So according to that, this size is more, this is less, and this is furthermore less. Now if they ask energy order in this, ReO4 will be more energy, TCO4 minus, then at last MnO4 minus. If they ask lambda max, just reverse it. If they ask oxidizing power, this will be more oxidizing power. If they ask reducing power, this will be more reducing power. And same concept here also you apply. From top to down, size will increases. So this will be less energy, this will be more energy. Here also this less energy and this will be more energy. So in charge transfer spectra, they may ask examples like which they may give a complex. They may ask whether it shows LMCT or MLCT, or they may ask this kind of questions. So this is about the charge transfer spectra. So definitely one question comes from this charge transfer spectra. I hope you understood. Thank you.